the previous video, we talked about how to calculate the pH of a strong acid. Now we're going to talk about how to calculate the pH of a weak acid. It's not as easy as calculating the pH of a strong acid, but it doesn't really involve anything new. We're just going to combine ice tables that we learned when we first talked about equilibrium with the ideas of pH and pOH, etc. So we know that weak acids do not dissociate completely. At equilibrium, we have significant amounts of reactant, the undissociated acid, still present. In fact, we have mostly undissociated acid present. Weak acids only dissociate a small amount. So if we have a generic acid, we'll call it HA, right? And I'll write the equation for its dissociation. And so if I want to know the pH, essentially I want to know what is the concentration of H3O plus at equilibrium. And so if they give us the initial concentration of the acid, right, we'll ignore the water because it's a liquid. We'll assume we don't have any A minus or H3O plus to begin with. So the reaction will have to go to the right. So I'll have minus X, plus X, plus X. And then I'll have whatever the initial concentration is, minus X, and then X and X for the A minus and the H3O plus. And so to get the pH, I need to know the equilibrium concentration of H3O plus. As long as I know the Ka for the acid, I can do an ice table problem in order to find the H3O plus, and then I can use that to find the pH. So let's do an example of this on the next slide. We want to calculate the pH of a 0.115 molar hypochlorous acid solution. And while they didn't give us the Ka directly, they gave us the pKa, but we can use that to find the Ka. So let's do that on the next slide. We have a little bit more room. Okay, as we said, this is going to be an ice table problem. I'm going to need to know the equilibrium constant, so why don't we go ahead and do that first. So we have the pKa, so we know that Ka is 10 to the minus pKa, so the Ka is 10 to the minus 7.54, or that is equal to 2.88 times 10 to the minus 8. All right, we set up the ice table in the last problem, but let's go ahead and do it again more formally. So we have, now we know our acid, so we'll call it HCIO. We'll react with water to form the hypochlorite ion and the hydronium ion. I'm going to go ahead and erase that Ka work to give us a little bit more room. I'll rewrite the equilibrium constant. All right, so we found that Ka 2.88 times 10 to the minus 8. All right, so continue to work on our ice table. We don't care about water. Cl minus and H3O plus both start at 0. We have 0.115 for the HClO. Fill in our change row. All right, so we'll go ahead and plug this into our equilibrium constant expression. All right, now at first glance, we're going to have x squared over 0.115 minus x. And so this looks like a problem where we would have to solve the quadratic equation. However, as is the case with pretty much all weak acids, for the strongest of the weak acids, we can't do this, but for most weak acids, right, the equilibrium constant is very small. And so we can apply the K is small approximation, right, and that will allow us to ignore the minus X in the denominator. So that'll greatly simplify our solving of this problem. So I'll multiply both sides by 0.115. And so on the left, that gives me 3.32 times 10 to the minus 9 is equal to x squared. Then take the square root of both sides. So that gives me x is 5.76 times 10 to the minus 5, right? And x is our H3O plus concentration. So to get the pH, I just need to take the negative log of that. And so then that gives our pH, which is what the problem was asking for, of 4.24. Okay, I just wanted to do one more example. We just saw how we could calculate the pH of a weak acid solution, but really all of the equilibrium problems that we did last chapter can be applied to weak acids. And so let's do one more example. So we have a 0.250 mole sample of some generic acid called HX. It's dissolved in enough water to form a 655 milliliter solution. And they give us the pH and they want to know the Ka. And so to give us more room, I'll set this up on the next slide, but this is just another ice table type problem. Okay, so let's start out by going ahead and setting up our ice table. Now, to find the initial concentration of HX, I have to do a little bit of work, because they gave me the moles and the volume, but not the molarity. So remember to convert your volume into liters. And so our initial concentration is 0.382 molar. Of course, the water, because it's a liquid, doesn't concern us. These initials are 0. Fill out our change. All right, so to calculate Ka, I need to know what the equilibrium concentrations are. And it appears right now I don't know that. However, we know the pH. And so I can use the pH to find the H3O plus concentration at equilibrium, right? And so that will give me X. And then once I know X, I can recalculate all of these equilibrium values, and then I can plug that into the equilibrium constant expression to get Ka. So, of course, to find the H2O plus concentration, I need to do 10 to the minus pH. And that gives me 2.88 times 10 to the minus 4. And so that is X. So I'm going to go ahead and just plug that into Ka. Right, so we know that Ka is equal to, it's going to be X squared. So I'm going to have 2.88 times 10 to the minus 4 squared divided by 0.382 minus 2.88 times 10 to the minus 4. And to the 3 decimal places that we have, that's actually not going to change the 0.382. So, but I guess it doesn't really matter. We can just go ahead and calculate it. Just put the numbers in. And when I solve that out, I get my Ka to be 2.17 times 10 to the minus 7.